Good morning, everybody. Thank you for being here today. My name is Ana Diaz, and I'm happy to be your host for today's webinar. As you may know, this webinar is organized by the Entails EU project. And today we are going to talk about how to turn industrial byproducts into new opportunities. We have a lot to share, so we are going to start now. First of all, please let me briefly introduce myself and Innovarum. As I said before, my name is Ana Diaz. I am a biotechnologist and I work as an innovation consultant at Innovarum. Innovarum is a consultancy company based in Madrid, and we are specialized in driving innovation into the agri-food and the bioeconomy sectors, with more than 10 years of experience. We have proven success story in Horizon Europe, and also we are a highly professional team of 15 people. Regarding our services, we cover a lot of activities regarding innovation in the agri-food sector, and we offer innovation consultancy specialized studies. We write proposals for EU projects. We offer external dissemination and communication services, and we also participate as communication, dissemination, and exploitation partners in several collaborative projects. One of those projects is CEARS project, as we are leading communication task, and that's the reason why we're here today. So let me briefly introduce the agenda for today's webinar. We started at 11, and after this brief introduction, I'm going to give an overview of the CEARS project, and then we are going to have two expert talks. The first one is going to be given by the Institute of Sustainable Processes about how to transform methane into cosmetics products. The second one is going to be given by INEA, and it's going to be about how to recover and purify valuable composts from fermentation broths. Both are key partners at CEARS project. And after the two expert talks, we are going to have some time for the audience to ask questions. Then, in the second part of the event, we are going to have a discussion panel about the revalorization of industry byproducts into new products. This is going to last about half an hour. And then we are going to have a second round for questions. We are going to give the audience some time to ask questions in the chat. And then we are going to close the event at 12:30. Now let me explain to you how to participate in our webinar. First, I wanted to let you know that this session is going to be recorded, but only for dissemination purposes. And to ask your questions, we are going to ask you to use the chat and not the microphone. We are going to have two slots of questions after a project presentation and then after the discussion panel. And now, after this brief introduction, I'm going to give an overview of what is CEARS project about. Well, CEARS project started in 2022 and is going to last 4 years until 2026. It's coordinated by Mau San Miguel, which is a lead company, beer company here in Spain, and it has a budget of more than 7 million. We are a diverse consortium of 12 partners and one linked third party, and we come from 5 different countries, which are Spain, Portugal, the UK, Germany, and Switzerland. So what is CEARS project? Well, the main goal of the project is to revalorize beer industry byproducts into high 5 added value industrial byproducts. And this project also follows a biorefinery approach. This project is not only focused on developing sustainable products, but is also focused on covering wider impacts, such as improve the environmental impact of the beer production chain, improve biodiversity, and also improve land use. To obtain these bio-based products, the CEARS project follows a biorefinery approach and is currently developing 2 different production platforms. The first one is the insect platforms and aims to upgrade bagasse into insect protein to obtain protein drinks. The second one is the microbial platform and aims to convert CO2 into caproic acid for the development of animal feeding products, also CO2 into chlorine for sanitizing products development, also biogas into ethylene for cosmetics products development, and also biogas into single-cell protein for pet products production. Each of these value chains aims to have positive impact on the environment, and aims to reduce the carbon footprint by 45%. If you want to know more about Cheers project, please feel free to check our website, follow us on social media, on X and LinkedIn, when we regularly publish about project updates, project progress, project events, such as this event. And also with this QR, you could subscribe to our quarterly newsletter. And now I'm going to conclude my presentation here, and I'm going to give the floor to Andrés Felipe Torres, who is an assistant professor at the University of Valladolid, and also is a researcher in Cheers project, and he's going to talk about how to convert methane into cosmetics products. If you could share your own slides, I will appreciate that. And thank you very much for being here with us.
Hi. Everyone is seeing the slides? Yes. Yes.
Yes, we can. Thank you.
Yes, thank you. So, hi everyone. I'm very honored of being here, presenting this presentation, sharing the screen with so recognized researchers and practitioners in the wastewater treatment field, and also watching so many participants, many of them which we are friends. This presentation was originally prepared by Raquel Herrero Lobo, who is a PhD student in our institute, but unfortunately she is right now on a medical leave, so I expect to cover well her back. Well, our presentation is called Boosting Sustainability, Biotransformation of Methane into Cosmetic Products. First, a quick view of our institute. We are part of the University of Valladolid, and we are a leading institute in research and development of technologies for the conservation of the environment and the advancement of sustainable industry. We had pretty good numbers in our scientific output, and we are involved and being involved in several regional, national, and international projects, including the Cheers project, which is an EU Horizon project. We have 4 research areas, including clean environment, green energy, resource utilization, and clean, optimal, and efficient industry. Well, a short summary of our presentation. First, we will visit some ideas on the side stream in breweries, which are ultimately our sources for obtaining viable byproducts. Then we will check some concepts on methane bioconversion into ectoins. Then we will show some detailed results on our efforts on large-scale optimization of Taylor flow reactors and the process of scaling up these reactors to an industrial level. And then we will withdraw some conclusions. First of all, breweries are a huge industry, and Majo San Miguel, which is the core of the Cheers project, is a pretty nice example of a huge industry. And also the plant of aloe vera in Madrid is a huge industry. Majo San Miguel produce important quantities of spent grain and yeast per year, which are in the Cheers project will be valorized through the production of insect protein. But in the line of ectoin, we are concerned about wastewater, and more than 1 million tons of wastewater are produced in the plant of Majo San Miguel, which are currently being treated by anaerobic means, producing more than or almost 10,000 tons of methane per year, which constitutes a huge, tremendous opportunity for obtaining methane-related byproducts. Of course, that in a context where where we have very competitive prices of energy, wind and solar energy, the search for new alternatives for methane valorization is quite relevant. Well, methane can be bioconverted into ectoins due to the activity of methanotrophic microorganisms that, in the presence of high salt concentrations, accumulate ectoin and hydroxyectoin to protect from the salt stress. So these microorganisms can become a microbial platform coupled with anaerobic digestion, producing these ectoins and CO2. Ectoin is and hydroxyectoin are very interesting molecules. As I said, they protect against salt and in general oxidative stress. So they are very, very relevant as a bioproduct. They have a elevated market price of between or at least 600 to 1,000 euro per kilogram. And when used as an ingredient in cosmetic preparations, ectoin and hydroxyectoin can protect and contribute to stabilize macromolecules such as DNA, lipids, protein. It offers against protection against radiation. So these are good reasons why these molecules has a lot of application in pharmaceutical and cosmetic industries. However, in the we have like the upstream and the downstream processes. So in the upstream process, we accumulate ectoin inside the cells, but we still have to separate this ectoin from the biomass. So we have the process called biomilking, which consists basically in two centrifugation cycles. In the first one, we separate the biomass from the salt medium. This biomass is then resuspended in a salt-free water where the cells will release the ectoin because they don't need more this ectoin to protect against salt stress. And then in a second centrifugation cycle, we have in the supernatant the ectoin solution, and then in the pellet we have the biomass that can be recycled to the process because the biomass doesn't suffer any lysis or stress during these centrifugation cycles. In previous works, some colleagues have demonstrated the techno-economic feasibility of this process. For example, in this paper by Victor Perez, he analyzed the conversion of or the production of 10 tons per year of purified ectoin, and he identified, of course, high investment and operating cost, but also due to the elevated price of ectoin in the market and the cheap cost of methane, he actually identified a very good profitability with a payback time of some 3 years and an ectoin production cost of about 200 euro per kilo, which offers a pretty good margins. Well, regarding the optimization of Taylor flow reactors and the scaling up of the process, the main issue here is that methane is an hydrophobic gas, so we need reactors that can increase the gas liquid transfer. And the Taylor flow reactors are a pretty good opportunity for this enhancement, since they consist in capillaries, very thin capillaries between 1 and 5 millimeters in diameter, in which the gas bubbles and the liquid slugs are organized in co-currents. So this organization creates a high interfacial area, thus a high gas liquid transfer. And actually the mass transfer coefficients of these reactors are of at least 1 order of magnitude higher than similar reactors in terms of energy inputs, such as the column bubble reactors. So in a research group and as part of the SHEARS project, we have focused in the optimization of the operation of these reactors for the bioconversion of methane into ectoin. So we have developed 3 sets of experiments. In the first experiments, we optimize recirculation gas and liquid recirculation flow rates and also capillary lengths. And a second experiment, we optimize biomass concentrations at different gas resident times. And in a third experiment, we assess the effect of semi-continuous biomilking and semi-continuous extraction of ectoins in the bioconversion of ectoin. The first 2 experiments are part of the PhD of my colleague Raquel. We use the lab scale unit for the Taylor flow reactor, which is a unit with 25 glass capillaries of 1.5 meters of length. These capillaries interconnect to vessels, which everything goes to our volume of reactor of about 7 liters. We fit this reactor with current with methane at 5% concentration. We inoculate the reactor with a methanotrophic consortia in a salt media of more or less 6% concentration of salt. So quickly, our results indicated that when we increase the gas recirculation rates, we were able to increase the methane bioconversion efficiencies. But we lose some capacities when we increase the gas retention time, of course, because we were feeding less mass of methane to the reactor. And also the increase in gas recirculation rates increase the osmolyte productions. So what we conclude here is that when we put more methane in the recirculation, we improve the contact of methane with the biomass, thus increasing the efficiencies and increasing the production of osmolytes. The results are published in the Journal of Environmental Chemical Engineering, so you can check the paper for more details. In the second experiment, we assessed different or increasing biomass concentrations, and what we saw here is that only at very low biomass concentrations we observed a biological limitation of the process. So this is interesting because it means that we can operate the process at least up to 2 grams per liter without affecting bioconversion efficiencies. And this means that, of course, more biomass concentrations at the end means higher hectare productions. These results are also published in a new paper in the Journal of Environmental Management, and of course you can visit the paper to see more details. And in a third experiment, what we did was to perform semi-continuous extractions of different ratios of culture broth, up to 70% of the culture broth, and we conducted these volumes to biomilking, and we recirculated the biomass to the reactor and assess the effect on bioconversion efficiencies. We saw that after a prolonged time of almost 60 days of operation, we saw some decrease in the bioconversion efficiencies, but that were also related with some losses of salt after so many cycles of biomilking. So from this experiment, but of course, when we increase the volumes of cultivar that were biomilking, we also increase the quantities of hectones that were produced. So the important thing here is that we confirmed that this number of 40 milligrams per hectare can be produced per kilogram of methane fed into the reactor with few losses in the bioconversion of methane. After these experiments, we enter in the process of scaling up the reactor. So we were trying to move from a relatively short reactor from 25 glass capillaries, which was the reactor we use in our lab scale experiments, to a more compact reactor. So we have a first prototype of 200 glass capillaries embedded in a plastic tube with the same area of the glass capillaries of the lab scale unit. And also we moved to the use of ceramic modules, which are produced by Corning and has applications in other industries, but that can work well as capillaries. And in the same area, we can have up to 470 capillaries. So considering this high number of capillaries, we moved to perform some abiotic tests, mainly aimed at confirm the high gas transfer characteristics of the reactor, and we achieved pretty nice results, increasing up to four times the KLA of the Taylor flow of the glass capillaries prototype that we use in the life scale experiments. So considering these good results, we move to complete the instrumentation to operate this reactor for the bioconversion of hectoine. Here you can check the high turbulence in the reactor. And from these lessons, we moved to the design of the industrial or semi-industrial prototype that will be installed in the demo site, which consists on almost 40,000 capillaries, also ceramic capillaries, and that is already under construction by our colleagues from CISPRO. This reactor will treat, we have the capacity of 1 cubic meter and a volume of reactor of 1 cubic meter, and will be able to produce up to 20 kilograms of hectane per year. With our colleagues from Virginia, we designed all the downstream processes, which has a capacity to treat at least 200 liters of filter broth per day, and which consists basically on electrodialysis and ion exchange columns. So as conclusions, well, we can achieve very high bioconversion efficiencies, always at the highest gas and liquid recirculation flow rates, and a residence time of 2 hours. The biological limitation of the biomass occurred only at very low biomass concentrations. And with the biomimicry experiments, we confirmed that good productivities of hectane can be obtained per kilogram of methane fed to the system. So thank you very much for your attention. And of course, the acknowledgement to our funding institutions.
Thank you very much, Andres, for your presentation. It was very comprehensive. And also it was great to see such a good efficiency on the conversion process, and also to see that this biomilking and the Taylor flow reactor are not only technically, but also economically viable. So this is very good. Thank you so much. Now I'd like to remind you that we are going to have a second expert talk, but if you have any questions, please feel free to drop them in the chat, as we are going to leave time after Jorge's presentation. So now I'm going to give the floor to Jorge Garcia, who is a project manager at INEA, and he's also coordinating INEA's efforts in TIRS project. You can turn on your camera and your microphone, and thank you very much for being here. Thank you.
Hi, good morning, everyone. Thank you very much for your kind presentation. Now I'll be presenting our work on the design of an integrated downstream processing for recovering and purifying specific volatile fatty acids from fermentation as part of the TIRS project. Okay. Here is an outline of the main concepts I will talk about during this presentation. But first of all, please allow me to introduce INEA. INEA is a technological center dedicated to innovation and development in the food, packaging, and bioeconomy sectors. INEA is committed to enhancing the competitiveness of companies through cutting-edge research and technological initiatives, thus contributing to the advancement of sustainable practices in various industries, as you can see in the picture. The key figures for INEA along the 2023 are displayed in this slide. And as you can see, we have a significant involvement in R&D projects with a particular focus on circular economy, sustainability, and economy approaches. Today, I will focus on the TIRS project. But which is the role of INEA here in the TIRS project? As was outlined in the previous presentations, these are the main diagrams illustrating how technologies have been applied to obtain 5 innovative bio-based products from underuse and waste side streams from Mouse Brewery. This project is a notable example of a top-down biorefinery approach. Starting from raw material to produce a target byproduct, each step is designed to reduce impurities and optimize purity and recovery, ensuring a sustainable process that yields a valuable and marketable product, aligned with the principles of efficient bio-based production. INEA has played a pivotal role in the TIRS project, as demonstrated here, as you can see in the slide. Our involvement includes the co-design of the pilot plant of the caproic acid-based feed ingredient and the subsequent validation with Henia Bioenergy. Furthermore, we are involved in the whole value chain of insect and cell and single-cell proteins, currently focusing on downstream process at a demo scale. About the elongation process, as you can see now, during the microbial chain elongation process, organic waste streams are initially transformed into acetate. Subsequently, this acetate is converted through different microbial pathways into caproic acid or caproate, a compound that is regarded as being of greater value than acetic acid. Caproic acid's importance extends beyond scientific interest, driven by rising demand for bio-based chemicals, for example. Its organophilic and antimicrobial properties support diverse industrial applications, including its use, as you can see, as a precursor in plasticizers, esters, detergents, solvents, so on. It plays roles in pharmaceuticals, food and beverage, personal care products, and eco-friendly lubricants, especially in flavor, fragrance, and aroma formulations. Market growth is fueled by emerging economies, though challenges remain due to volatile raw material prices, very changing in this moment, and also the stringent environmental regulations. Subsequent to microbial chain elongation, the overall composition of the broth is presented on the slide. As I mentioned before, the objective of this procedure, of this DSP, is to recover and purify this volatile fatty acid mixture in order to produce a marketable product suitable for use as a feed ingredient. But what is the DSP, the selection and the design of it? In the context of biotechnology, upstream processing refers to the initial phase of biomanufacturing, which covers all the steps involved in the cultivation and growth of biological entities. This pivotal stage entails optimizing conditions to enhance productivity of the desired bioproducts while upholding purity and quality, as you can see in the previous presentation. The process typically involves the selection and development of suitable cell lines, the preparation of growth media, and the management of bioreactors under carefully controlled conditions. Otherwise, the downstream processing stage follows the upstream processing and is a critical and highly specialized component of bioprocess engineering. It covers a series of unit operations that are designed to separate, concentrate, isolate, and purify this target bioproduct or bioproducts from complex biological mixtures. The purpose of this DSP is to recover and refine this product, ensuring it meets the necessary quality to be used, to be sold, to be processed, and regulatory standards. The complexity and nature of the processing broth, as means the impurities, dictates the number of steps involved in the DSP, which in turn involves a range of downstream processes, downstream technologies, that are adapted and tailored to suit the specific product in question. Here, you will see the first version of the DSP, where extraction was evaluated to release the caproic acid presented in the solid phase through sonication. The importance of this process lies in the chemical behavior of caproic acid, as I said before, because it's a highly hydrophobic compound that tends to associate with organic matter in the solid phase. The presence of unreacted ethanol can be leveraged due to its dual role as an organic solvent and also as an extractant. So caproic acid exhibits greater affinity for ethanol than for water or residual organic matter, so we can extract it. However, only a slight increase in caproic acid content was observed without pH adjustment, leading to the dismissal of this approach, due to the performance and also the cost involved. As a preliminary step in the DSP process, low-pressure membrane prepares the broth for further purification by removing any residual cell debris, colloids, and large particulates. microfiltration and ultrafiltration are both effective methods for achieving this, due to their ability to remove these impurities that are larger in size than the target BFA product. These techniques allow BFA molecules that are very small, to pass through the membrane while retaining larger impurities. The concentration of the BFA product involves removing water and small molecules in the broth, which reduce the volume of material for subsequent processing steps, such as spray drying. Concentrating the product and minimizing its volume is a common application of tight membrane technology in DSP. Depending on the characterization of the feed solution, either nanofiltration or reverse osmosis can be employed. The effectiveness of membrane processes can be enhanced through the implementation of cascade engineering, as evidenced in previous developments, but budgetary constraints limit its application. Spray drying is a more efficient and economical technique when the solid content is moderate, greater than 20% by weight. So this process needs membranes to be efficient, cost efficient. This method allows for the effective transformation of the concentrated BFA solution into a stable powder form. The final structure of DSP is displayed as a block diagram here. It consists of a centrifugation, followed by 2 membrane filtration steps connected in series, and finally spray drying. Now we are going to see a brief comparative of this DSP depending on the operating conditions. Operating at a pH of 5 or lower may result in the loss of some BFAs during the process due to their inherent volatility. As these BFAs mixtures passes through the membrane and proceeds to spray drying, there may be significant challenges. The composition of the product is somewhat unpredictable, being an undetermined combination of volatile and non-volatile species. The presence of a high quantity of water, coupled with the low solid content present in the stream, results in significant energy consumption to achieve a concentrated product. Overall, this downstream approach is energy intensive, highlighting the need for efficient methods to optimize energy while concentrating the product. In the event of a higher pH value, a high-quality permeate is produced, which can be reduced throughout the process, thus contributing to the overall efficiency and sustainability. The presence of BFAs in their salt species, such as calcium and sodium salts, acetates, caproates, etc., are larger and more stable molecules than their acid counterparts. This property facilitates effective concentration, separation, and purification through the utilization of size exclusion separation mechanisms that are the membranes. Nanofiltration is the most suitable process to implement this in this context, as it can efficiently separate and concentrate the BFA salts while maintaining their integrity. This configuration was selected to progress to the subsequent stages, which entail upscaling, construction, assembly, and commissioning of the demo plant, led by Genia. The conclusions. Okay. The suitability of the DSP system is defined early on by target purity, yield, and feed characteristics. Following microbial chain elongation, various separation techniques were selected for the continuity, efficiency, and cost effectiveness. The process includes centrifugation, microfiltration or loose ultrafiltration, nanofiltration, and finally the product formation through spray drying. Although initial results fell short, the modular, scalable DSP design allows for optimization via cascade engineering to meet the KPIs of a project. Thank you very much for your time, and we will see in the questions.
Thank you very much, Jorge. It was a very good presentation, and it was good to see the possibilities of downstream processes. It was very good to see how you are working on improving the efficiency and also to trying to make these processes less energy consuming and more sustainable. Thank you very much for the presentations. And now we have some time for the audience to ask questions to Andres and Jorge about their presentations. Let me share my screen. In the meantime, you feel free to drop your questions on the chat, please, and I'm going to read them. Okay, let me share my screen again. Okay, here we are. Okay, we have a question from the audience. This question is for Andres. What are the challenges or limitations associated with the biomilking process?
Yes, thank you to Antonio for the question. Well, from our lab scale experiments, what we saw was mainly a certain loss of salt after continuous centrifugation cycles. So what we did was to add more salt in order to maintain the target salt concentration of 6% in the bioreactor. But of course, with a prolonged operation of the biomilking, we will observe certain shift in the dominances of the microbial community, but without such a relevant losses as I show it in the bioconversion efficiencies or the ectoin production. So at the end, it seems that at least in the lab scale, the biomilking process is quite resilient, and without the proper adjustment of maintaining salt levels and proper operation of the centrifugation, it seems that it can be pretty efficient for the separation of the ectoin.
Thank you very much, Andres. We have another question for you. Who's the final customer of the Taylor flow reactor? Will it be an industry or both?
Actually, in the Shears project, we are more focused on producing ectoin. So the Taylor flow reactor is our mean to enhance the production of ectoin. But of course, that the Taylor flow reactor can be applied in many other processes. So I mean, the customers could be everyone who need a very high gas liquid transfer. But in the case of the Shears project, we are of course focusing in the ectoin market.
Okay, perfect. Thank you so much. Yeah, it's very good to see how this process is very versatile and could be applied to different industries. Also, we have a question in the chat regarding the downstream processes. How other process conditions, apart from the pH, affect the final yields for purifying volatile compounds?
Apart from pH values, the temperatures are very important due to, as you said, there are volatile compounds. So it's important to keep up with the temperature around milk conditions, around room temperatures in conditions like that, because membranes, for example, works worse when you have more temperature. The higher temperature larger the pores of the membranes and make them less efficient. So it's better to keep the temperature at room temperature or even lower than that. With other processes, for example, centrifugation is not very affected by the temperature, but spray drying is not affected at all because you have to increase the temperature. So the process itself will have an increase of this temperature to conditions about 100, 125, depending on the target compound. So normally here with the DSP we saw we will find problems with temperature in membranes mainly.
Okay, Jorge, thank you very much. Cannot see more questions in the chat. If you have, this is for the audience. If you have further questions, you can drop them now the chat. And also at the end of the event, we are going to give you some time to reply them. Well, I have a question myself for both of you. I'll ask you both talk about different processes to revalorize compounds from the beer industry, but I would like to ask you, what do you think are the challenges or next steps to integrate these processes in the industry? What do you think? Who wants to, maybe Jorge wants to take the lead on this?
Okay. Mainly, we should think that this process is oriented to treat underuse streams and also waste streams. So the regulations, the policy support, all the regulations is very important for us in order to know how we can apply this to higher industry or even higher customers than the project itself. So this part is very important. Also, guarantee that we have a continuous operation, a continuous processing is very important in this part. Also upstream and downstream, in order to produce more, to give more quality, to give a product that could be used in the market. So for me, maybe if you ask me a few minutes, I can give you more things. I think that these two challenges are the most important now.
Thank you very much for your answer. Definitely, I totally agree with you that regulation and policy is very important to move forward on this issue. Okay, we have another question in the chat. What are the unit economics on the process? I think maybe Andres, maybe this question is for you.
Is that I'm not really understanding the question. The unique economics. It's like
maybe the cost or
the cost.
Yeah, I think it refers to the cost.
Yes, probably is the cost. Well, in our preliminary analysis, we identified a production cost of hectane from methane produced by anaerobic digestion from wastewater of, as I said, about 200 euro per kilogram, which in a market where the hectane price is about at least 600 or very much euros per kilogram, it means that the opportunities for profit are quite nice. Of course, that it depends on the if this production cost can be maintained on an industrial level, which we expect to decrease with the scale factor, but also in the final purity of the product after the downstream process. So probably when we can operate our pilot systems in the demo sites of the Shears project, probably we will confirm many of these assessments. But the expectations are quite nice.
Thank you very much, Andres, and thank you very much both for your good presentations. I think they were very explanatory and comprehensive, and we learn a lot about how Shears project is advancing. I think if I I cannot see more questions on the chat, so I think we can move forward into the second part of the event, which is the roundtable. And I'm going to ask all our speakers to turn on their cameras and their microphones. First, I'm going to introduce the topic for today. We are going to talk about how unlocking the potential of industrial byproducts. As you all know, industry byproducts are very promising for both sustainability and economy, and repurposing waste materials such as the biogas, the CO2, and the methane we speak about before can significantly reduce the environmental footprint and also create new revenue streams with a very good positive impact on the economy. Normally, these products are discarded as waste, but they are very rich in nutrients and other valuable compounds that could be recovered. Therefore, transforming these currently wasted products into new resources could enhance sustainability, climate resilience, and economy. Now, I'm going to give an introduction to the audience on who our speakers are. First, we have Ruben Vera. He's the project coordinator of Cheers project, and he's coming from San Miguel, the project coordinator. And Ruben drives sustainability initiative with more than 7 years of experience in this field, in climate strategy and environmental impact. Then we have Jorge Garcia, who was one of our speakers. He's a project manager at INEA, and he's currently coordinating INEA's efforts in Cheers projects. Jorge is a chemical engineer with a PhD with more than 15 years of experience in R&D and specializing in environmental engineering. He's leading EU projects like Cheers, where he coordinates all the INEA's activities. Then we have Alba Ramos, who is a project manager at NATAC. And she's a biotechnologist and the project coordinator of the Sustain Next project at NATAC. And she brings academic and industry expertise in polyphenols and novel foods, with a strong track record in European R&D projects. Also, we have Raúl Muñoz from the Institute of Sustainable Processes from the University of Valladolid, also working in Cheers project. He's a professor at the University of Valladolid and an expert in environmental biotechnology. And also he specializes in biogas upgrading and algal bacteria wastewater treatment. He's published more than 300 papers and is a global reference in biological gas treatment. Now we have Amparo Jiménez Quero. She's coming from Chalmers University and she's the coordinator of Circle K project. And she's an assistant professor at Chalmers University, and she's currently leading EU projects on circular biomass valorization, turning waste into high-value and bio-based solutions for food, agriculture, and biomedicine. And we have Patricia Zamora, Patricia, are you here? I think, okay, she's having technical issues. Maybe she's reconnecting later, but let me introduce her as well. She's a senior project manager at Aqualia and is a chemical engineer with a PhD in analytical chemistry. And she's currently leading EU innovation projects in water treatment, reuse, and desalination. After this introduction, I think we can move on to the discussion. And I'm going to start with an open questions to all the speakers. Here's my question. How can circular economy principles could be better integrated into existing industries to optimize the byproducts valorization? Who wants to take the leads on this to break the ice? Okay, Ruben.
Okay, can you hear me?
Yes, we can.
Okay, first of all, I would like to thank to Innovarum team who have been working on the preparation and assembly of this interesting webinar. Well, starting with this question, the first and most fundamental thing is a shift in perspective. We need to stop thinking about waste and start seeing resources where we previously saw as a problem. In practice, this means rolling up our sleeves and first really understanding what we generate. In our case at San Miguel, byproducts like brewing spent grain or yeast are significant streams that we map and characterize thoroughly. Then R&D and eco-design come into play, researching what these resources can be used for, perhaps developing new products, or even slightly modifying our process to facilitate this future valorization. And something key, in my opinion, is to look beyond our own factory walls in terms of industrial symbiosis. What is a byproduct for us, like spent grain, can be an excellent raw material for animal feed, for generating energy, or even, as we are exploring, for creating new byproducts. All of this, of course, supported by the right technology and with a global vision using tools like life cycle technology, and with a global vision using this assessment in order to ensure the solution. Well, this is my opinion.
Thank you very much, Ruben. I think it was very meaningful contribution. I'm going to give the floor to Raúl. Maybe he can share his thoughts from an academic point of view.
Okay, sorry, I had the camera off. I don't know why.
No problem. We can see you. We can see you now. Thank you.
Okay, perfect. Now, I would like to highlight also in this particular question the potential of circular economy principles in the valorization of gaseous streams, since traditionally most of the attention has been given to solid waste or wastewater, and these gaseous emissions, we're talking about carbon dioxide, the lead emissions of methane, or even ammonia, they have a significant potential for carbon recovery, nutrient recovery.
Thank you very much, Raúl. Who else wants to take the lead on this? Maybe we can have new thoughts from other projects. Amparo? Please go ahead.
Can you hear me now?
Yes, we can.
No, I am just taking from what Raúl just mentioned. The way we are processing or the way we are producing right now is also changing, meaning this principle of bioeconomy has to be open to welcome other type of side stream and sources all the time. So I think it's nice to emphasize that I will also talk from the academic point of view. So we do things that they are in a very early stage, and we can already see some potential of how to valorize other side streams that they are not even produced at that high volume in the industry right now, but probably that will come in some years if we continue moving towards a more bio-based production. So I mean, the principles they are there is the integration of all value side stream and change into the production. But yeah, just having in mind that probably new ones are to come.
Thank you very much, Amparo. Alba?
Yeah,
Please
thank
go
you.
ahead.
I would also like to contribute with this previous comment from the other partners. So from our view, we are working in bioeconomy since the beginning of the idea of our biorefineries. That is actually our business model. So maybe there are some new opportunities in the industry not integrating this principle into a business already developed, but to including them since the beginning of the business model. So when we design this kind of strategies and the upcycling of our products, we are implementing these circular economy principles since the first design of this model. And I think it is key just to have this in mind for future industry that implement this kind of models, to have this like a core of the next steps, and not just to include it an additional point of the model. That is, it has to be the key, and in our industry is something essential to also deal with all the objectives we need to address.
Thank you, Alba. That's a very good point, and definitely to make a change, it needs to start from the beginning and from the business model. Any more contributions to this question? Maybe Jorge or Patricia, you want to share your thoughts with us?
Well, so I agree with Alba's comment. He's completely right in the sense that nowadays, I mean, integration of bioeconomy principles in the current facilities infrastructure is quite challenging. It's quite difficult. So, and this is one of to my opinion, is one of the obstacles that we have to face. So the concept of biorefinery has to be really taken into account since the very beginning, because otherwise it's not viable from either a technical and an economical point of view. And indeed, I mean, this integration has to be accompanied by a economic viability. This is quite important, because I mean, there is a lot of development, there is a lot of talking about biofactories, but to companies, to market, it is essential that it has to be competitive in prices with existing fossil fuels counterparts. So this is the key, indeed.
Thank you very much, Patricia. Definitely, what you say, it's a very good point, and there are many obstacles to make this a reality. That brings me to my next question, which is targeted to all of you. What do you think are the key regulatory or policy, or maybe other barriers for the commercialization of products derived from waste? What do you think? What are the main obstacles to this to become a commercial reality? Who wants to take the lead on this? Amparo?
Yeah, I guess I will start for something very obvious, and I think you even mentioned it. There is a lack on the regulation or a lack of clarity on how that can be driven back towards the production. And if you think about the food side streams, even though they have been produced within the food chain, in the moment that they are considered somehow waste, that means they are out of it. And it's almost impossible nowadays to revert that. Meaning, we will need, or I guess is what most of these EU projects we are aiming, is to also tackle towards the policymakers and try to ask for a more clear regulation to make the whole task a bit easier. Because of course we see the potential and the like the ambitions for many industrial partners to reconvert their side streams, so we can apport also the technical part, but the problem is they don't have the approval of putting that into the market directly. So I would say that could be one of the main obstacles.
Thank you very much, Amparo. Definitely, there's a lack of clear regulation to this issue. I can see a raised hand from Jorge.
Yep.
Will you share your thoughts
Yeah.
with us?
Also, like Ruben, we work a lot in the agri-food industry. So we have stringent safety regulations. For example, the novel food approval for upcycled ingredients is a very hard process. So this, including with the definitions that Amparo said, we have legal ambiguities and also a lot of prohibitions and all that stuff. So it makes this very difficult to accept the commercialization of these bio-based products. Also, not only the regulatory and policy barriers, we have also the perception of the consumer. It's very important for us because the consumer, the end consumer, the local communities who receive this must have trained in that in order to know the clarity, the transparency is important. They have to know the process, how this will has to be obtained, all these processes, all these regulatory barriers, all this value chain, all the stakeholders should be included in that in order to pressure the policy barriers to also to break down them and make this possible.
Thank you very much, Jorge. Definitely, it seems like the legal barrier is the most important here, but not only, as the consumer needs to be receptive on receiving these new products. Alba, will you share your thoughts with us?
Yes, I completely agree with Amparo and Jorge in both of their comments. From one side, the terminology or the classification of byproducts and waste is not clear, and there is a lack of a regulation regarding the valorization of these byproducts, because, for example, in our industry is key to use these byproducts and as raw materials. So from us, this could never be considered a waste, because it's our first raw material from our transforming processes, and to be converted into high added value products. The thing is that when you produce an intermediate product from other industry that then can go to other industry for valorization, sometimes you need like an intermediate process to maybe to clean the product or to convert them in other fraction that you can valorize, and this change just can make the difference between a waste or a byproduct. And from us, it is a real problem, because there is a lot of different byproducts that have a lot of potential, and they cannot be considered a residue, because it does not have a real impact of the environment, and they can have a lot of uses even in the food industry, that is the one with the highest regulation, or from our side that we also produce from the pharmaceutical industry that have really strict rules. And also talking about the novel food regulation, that is also something that affects our industry quite a lot. We need to deal with this issue frequently, because when we create new products that needs to go under the regulation, it is a really long process, really expensive, and there are a lot of companies that cannot afford to go into these long processes. So it is something that can really stop the creation of these valuable products, and maybe with an easier processes and regulatory barriers that are not so strict can be easier from the industry.
Thank you very much, Alba. Yeah, definitely this is a very long processes for companies who could really invest on this. So it will be very good if this could be better managed. Thank you. I can see a raised hand from Ruben. If you want to go ahead.
Yeah, following up on what Jorge and Amparo were saying, the truth is we encounter several hurdles here. Sometimes the very definition of what constitutes a byproduct and when it ceases to be waste isn't entirely clear in legislation, and that creates a lot of uncertainty. Furthermore, if you want to market a new derived product, for example, for food, feed, or cosmetics, you have to comply with very strict and specific sector regulations that aren't always designed for these new circular raw materials. Add to that the fact that the rules can vary between countries, even within the European Union, and scaling a business becomes very complicated. So sometimes even the consumer perception can be a barrier if we don't communicate well. In our opinion, we undoubtedly need a clear, more agile regulatory framework that truly incentivizes circularity.
Thank you very much, Ruben, for your insightful contribution. Patricia?
Yeah, well, in addition to what the other presenters has mentioned, so I think That's very important to define where the added value of these bioproducts come from. And I mean, we do have in the market already, 16 products, very competitive in price. If the added value doesn't come from the decrease in price, we have to of the carbon footprint, but maybe for industry this is not enough. I'm talking, for example, for PHA. So PHA right now from biomass from other sources is not. It's not economically competitive with commercial PHA. So the added value comes from the fact that they have improved properties, mechanical properties, besides the reduction in carbon footprint. But this has to be perceived by the final users, by the consumers, So that's nowadays. If the price is not the driver, it is very difficult to appreciate the added value. The mindset has to change. Maybe in northern Europe countries they can deal with that, but in a globalized world, price is a driver, and we all know that.
Thank you very much, Patricia, and thank you all for your contributions to this question. I think they were all very meaningful, and we can conclude that definitely the regulatory framework should be improved if we want these byproducts to reach the market properly, and also price is a major barrier as well. Okay, so that takes me to my next questions, which is related to what Patricia said regarding the price of these products. How do you think business can balance the economic viability and sustainability when investing in these byproducts valorization?
Well, this is a question for me.
It's for everyone, but this
but I represent Mau San Miguel, so this is undoubtedly the $1 million question for any company. For us, it's not so much about balance, but about seeking synergy. It's true that investing in valorization can have an initial cost, but you have to look long term. Think about the savings from not managing waste, the potential new revenue from selling the valorized byproduct, improve efficiency, reducing your carbon footprint, and also the value for the brand, and reducing future risk. For this to work, the economic analysis has to be comprehensive, including those intangibles. And of course, viability heavily depends on whether you can scale the technology, and if there is a real market for that. This is where grants, initiatives, and green financing come into play, which can provide a significant boost at the beginning. But for example, at Mau San Miguel, we look at every project of this type through that dual lens. It has to be good for the planet and make business sense. This is very important.
Thank you, Ruben. Definitely, this is all about a balance. Does anyone else wants to share their thoughts with us? Maybe from the industry point of view, maybe Patricia or Alba?
Sorry.
No.
Thank you. From our view, it is also similar to the previous comment. So is coming to find a synergy between both aspects, because sometimes you need an initial investment to achieve this sustainability criteria, and that you really need to be competitive in these industries, but also it's something that is perceived as a benefit from the consumers or the client you are going to address. The thing is that maybe these benefits can be in a medium long term, in not really short term, but it is also talking about your image as a company and the setting the rules you want to compete after that. I think sustainability is now essentially something that you need to address. Mandatory is not an option, and if you are working in the food industry or even in the other kind of related industry, it is something essential to include it in your model. But for sure, it's also have a lot of benefits that can also benefit not only the image or the impact you have in your clients, but also it can be combined to make your processes also more efficient. And it is also will be translated after that in a more economic benefit. So it is not easy to find a balance, and sometimes it requires this first economic effort, but I think after some years it can be traduced into a lot of benefits for a company.
Thank you very much, Salva. Patricia?
Yeah, well, balance the viability with sustainability also stripes in the fact that the companies or industry have to monetize also not the net of the real economic value of the bioproducts. I mean, yes, it's cheaper. Let's say it's also there are also another impacts related to the image of the company, to corporate social responsibility. I mean, communication, dissemination. I mean, also they have to monetize that because there's a value in that. So this should be also taken into account. So it's not only about this is business and we have to make it cheaper, we have to be more competitive, we have to save costs, whatever. Yeah, that's true, but there's also another perspective that, but it has to be understood also, but from the boards of the industry and also for the consumer. So they have to learn to appreciate all these another impacts, because there are real impacts and there are impacts that also give money, that has to be monetized. This is also a very important point to be taken into account. But right now, I think it's try to balance both of them. It's tricky. It's tricky, and as Alba said in the very beginning, I mean, the inception of a business plan, has to be done with this idea since the very beginning. Okay, to balance, but also to industry, to industries, who have to make it then aware that sustainability is also a source of money.
Thank you very much, Patricia, and thank you all for a good contributions. We reviewed what are the main challenges for the regularization of bio-based products. We also discuss a bit about the business balance between economy and sustainability, and that's this good panel, as you all know, is from both academia, research, and industry. Takes me to my final questions for all of you, and with this, I think I can close the panel. How can academia and industry work together on this issue, on the byproducts valorization? On this question, I will be very happy if I could hear all your thoughts about this. Raul, you want to take the lead?
Okay, I can start. As a member of the academia, at least maybe also INEA is also doing some fundamental research as us, and most of the people in technology centers like INEA probably come from academia. The first thing is like, we must adapt our research to the needs of industries. I mean, we cannot do research with public money that is not relevant to society and to industry. This is the first thing. I mean, we need to do research that can be scalable and can be turned out into a service, a product, or a real benefit to society, talking more on social sciences. And this type of projects, the innovation actions like Cheers and maybe Flagship are the perfect framework for collaboration, where some of the successful research that we have validated in the lab are brought together with technology manufacturers like INEA or CISPRO or Genia, and also with the industry that generated by product like MAO, in order to make product valorization a reality in the future.
Thank you, Raúl, very much. Jorge, you want to take the lead?
Yeah, as Raúl said, our customers are the society and the industry. Collaboration can take form of joint R&D projects, where academia provides cutting-edge research, as we observe, and industry offers real-world testing facilities. We have the testing facilities there, so we must use it. Also, the technology transfer is very important in order to be applied in the industry. We can't have some experiments, some setups, we can test it, but we must think about this technology transfer in order, like companies like Equalia, like MAO, can apply it to the real world in order to see, as we can discuss before, we can see that we can balance this, as you said, the sustainability and also this economic viability. We can play with it, but we must play with our head, in this case, with some responsibility in order to make this technology transfer to them.
Thank you very much, Jorge. Ruben, you want to go ahead?
Yeah, our vision as a company is that working together with academia and research centers is essential. Achieving that viability and overcoming many of these barriers requires collaboration, especially between academia and industry. In my opinion, it's a perfect symbiosis. Academia brings cutting-edge knowledge, disruptive ideas, and industry brings the real-world challenges, the experience in scaling processes, and market access to the table. And maybe the question is, how do we do it? Well, through joint R&D projects like those funded by the European Union, open innovation platforms, creating joint research units through industrial PhDs, and facilitating technology transfer. The important thing is to have a smooth communication, mutual trust, and for both sides to understand that we need each other for innovation to truly transform the industry.
Thank you very much, Ruben. Amparo, would you be happy to share your thoughts with us?
So, I mean, I'm Spanish as you are, but I'm working in Sweden. And something that, for instance, is a bit different is in the education point of view. What we give at the university to not just PhD students, also to our master or bachelor students, is a very clear idea of how you can implement research or your knowledge towards an industrial application. So I think that also opened the possibility of not just answer to current questions that the industry have, but also use research to generate new knowledge or to generate other type of production or other type of companies in the future. So I think it's also part of what education should be evolving towards that, and making people understand that they should utilize what research is given. So I totally agree with Raúl that we need to take into account the impact over the society, but there is also a space or balance to do fundamental science that probably will bring to new solutions to the society. But of course, that is my point of view from the academy, and as I say, from Sweden, that there is a lot of support for entrepreneurship within young researchers, for instance.
Thank you very much, Amparo. That was a very meaningful contribution. I don't know if Alba or Patricia, if you want to share any thoughts on these questions? Or...
Yeah, I think the key, I mean, I couldn't agree more with Raúl's opinion, because this is one of the keys. The keys had the change in the conception of research at universities has to completely change. I mean, otherwise, this is the very, very beginning. This is the seed. And well, indeed, I think, to my opinion, the technology transfer and the communication between industries and research centers, university, has been much more facilitated. So right now we are, I think, in a step forward, compared to decades, but there still is a way to go. And I think that also, public entities, European Commission, or the entities that the funding entities, they have also to encourage this technology transfer among universities or research centers and industries. With proper plans, with proper actions. Because it's for universities and research centers, it's very difficult to take the lead and to the step, from the lab to even the pilot stage. It's quite difficult for them, because this is not their ambience, not their environment. So we have to implement tools for universities and also for research centers to take the lead and go to industries and to have the means for this first step, maybe communication. And so because for them it's quite a new world. So the scientists, they're not engineers, so there's a gap maybe in this first step, in terms of engineering, in terms of procurement, in terms of and we have to strengthen and try to fill the gap as much as we can. And I think public entities has a decisive role in this regard.
Thank you, Patricia, very much. We are running out of time, so I don't know, Alba, if you want to close this question with your intervention, that will be very appreciated.
Yes, thank you. Yeah, I completely agree with the rest of the panelists. So it is essential, this collaboration between academia and industry, generally to go and to move forward in research and innovation, but especially it is essential if you want to build the perfect consortium in this kind of projects. When we are able to share our different point of view, I think we generate this like a synergistic action. And sometimes it is a pity that in the academia they generate a lot of knowledge that will be really useful and that have a lot of potential to be a solution in the industry, and sometimes it doesn't really get until the end for different communication problems. And in this kind of project, it is good to know that we can have access to this knowledge, and then we can help from the industry to implement this solution in an pilot or industrial environment. So to be like much more close to the reality that they can be in this first step of development.
Thank you very much. Thank you all for your meaningful contributions to this panel. I think we can close the panel here, and that our main conclusions are that there's a potential market for bio-based products for waste. The regulatory constraints are the major at the moment, but the communication should be improved to improve consumer awareness as well. And definitely the collaboration between academia and industry is highly needed to become a reality. So there's no questions on the chat. I think we can conclude the event now. So I would like to a very big thank you to our speakers and to our panelists. Your contributions were very good, and I think we achieved to have a very meaningful discussion. And also a very big thank you to the audience for being here today. And also thank you to my colleague Daniel from Innovarum, who organized and covered the event, who is here with us as well. And I hope to see you very soon. Have a very good rest of the day.
Thank you very much.
Thank
Bye-bye.
you.
Thank you.
Thank you very much.
Thank you very
Bye.
much. Bye.